So this topic today is segment trees. And what we'll be doing is understanding them at a deep level. So I'll be discussing a few things about segment trees. The first one is range queries, right? And range queries like sum, or I'll just call it f of a range x to y, where x and y belong in the array, so 0 to n minus 1. Okay, so this is the first thing that we'll be doing. And the second thing will be lazy propagation. Lazy propagation basically means that you need to update, which is, let's call it u, an entire range, x to y. And this will be, let's say, add 1 to all the elements between x to y, and subsequent functions, function calls of x to y, which is getting the sum or getting the product, let's say, have to also be done quickly. Okay, so two types of queries in the range queries. We also need to allow lazy propagation. That's what we'll be studying. And we'll start slow, understand the scenario where a segment tree is used, and should be fun. So I'll just open the chat now, and you can all see the chat now. And you can see my reactions to the chat. Okay, please remove the chat section. Or can we discuss kth minimum unsorted array? All right, so segment trees it is then. Okay. So starting off, usually the way that we identify a question requires a segment tree is if you're given a question like this, where you have range queries, right? So maybe you're given a question, for example, you have an array A from of size n. So this is the n minus 1th index, and this is the 0th index, this is the first index, and so on and so forth. You have two types of operations. The first one being an update operation, update element at x to y. And the second type of operation is query element from x to y. So this does not make sense. So instead, we'll have something which is a aggregation operation. Given a range x to y, give me the sum of all elements in that range. Now, if you had been here for the last live chat that we had, we did discuss range queries, and they were exactly as mentioned here. However, this time what we are going to do is solve them using segment trees, which are a more efficient way of solving these kind of problems. If you have q queries, each query will take you log n time, and therefore the overall time complexity at the end of this should be q log n. Previously, we had discussed square root decomposition, which takes, for q queries, it takes q into root n time. So per query, it had root n time complexity, and the order complexity came out to be this. Okay, is this point clear? Like, is everyone understanding why we would need segment trees? All right. Rajat says yes. I take that as a yes for the 110 people watching. That's how classrooms work, don't they? Okay. All right. So when we're given these kind of queries, there's one brute force approach that we know. I won't be discussing it, but the basic approach is you just head in the range from x to y using a for loop, and the time complexity for this is at most order n, because the range might be encapsulating the entire array. And if that is not the case, if the range is, or rather if the query is of the type of update, then it's order 1 operation. However, we have to take the worst case into consideration. So what we'll be doing is we'll assume every query is going to be a range query for the entire array, and that is q into n. You could optimize it for for a range query by doing something called prefix sums, like we discussed in the previous live video. But even this, in the worst case, just flips the update and query time to order 1 for the range queries and order n for the updates. So it still remains worst case order q into n. So that's bad. And what we want to do is we want to reduce the worst case time complexity, because if q is of the size 10 raised to power 5 and n is of the size 10 raised to power 5, then q into n is 10 raised to power 10, and the processors being offered by compared programming sites run 10 raised to power 8 computations in 1 second. And the whole purpose of this is to complete 10 raised to power 5, 10 raised to power 5 with constraints q and n within 1 second. Okay, so what are the possible algorithms that we could use? We could use q root n, like we discussed previously, square root decomposition. But what we will be using this time is segment trees. Okay, so that is the reason why we will be using segment trees. Now let's get to the algorithm. I think segment trees are discussed a lot. A lot of you might have already heard of it, but what I'm going to try to do here is to explain the concept in such a deep level that you don't forget it the next time you try to solve a segment tree problem. Also, you can then use this as a base concept to solve a variety of problems which can be solved. Which require um, range queries to be answered. Okay, so let's imagine our array, instead of being a big block, to be elements, spread out elements, and I'm going to be giving them values. I'm going to give them a value of -1, 3, 7, 2, 4, 8, -1, 0. And if we count the elements in this array, it's going to be 8 elements, I think. So that's 1, 2, 3, 4, 5, 6, 7, 8. Yes. Now, the thing is, I'm going to be given range queries from X to Y, and this is my problem. The range queries are the problem. The updates are really fast. Updates are order 1, right? So I'm not so interested in converting A of X to I and trying to optimize this a lot. I'm mainly concerned about optimizing my range queries. If I could reduce the number of computations required when I am answering a range query, I should be good. I should be able to do well in this contest. So what I'm going to try to do is condense the information of these nodes into smaller nodes, into simpler nodes. Now, imagine a tree structure where every parent answers something. So what does it answer? Let's take the first two guys over here and let's assign them a parent. Okay, binary trees is what we are comfortable with. So binary trees is what we will be using. -1, 3 have a parent. What should this parent answer? It should be able to answer something which is relevant to what will be queried. So the range query, and I'm going to be assuming the range query is a sum query from X to Y. So give me the sum of all elements between 1 and 2. That's what this parent will be able to answer immediately. And to do that, it needs that sum. So it is -1 and 3, which is 2. Okay, this is the sum of all elements between 1 to 2. I'm taking 1 based indexing. You can take 0 based, and it's just the same. Similarly, I'm going to be assigning a parent to these two elements, 3 to 4. 7 plus 2 gives you 9. And going ahead, I'm going to be giving a 12 over here. And -1 and 0 give me -1. This looks good. And we can go on up the tree and assign similar values this way. But when we do go up the tree, what we need to understand is, how does this node answer for the tree? I mean, what is the responsibility of this node? The responsibility of this node is the cumulative responsibility of these two nodes, which is in turn sum from 1 to 2 plus the sum from 3 to 4, right? So basically the sum is from 1 to 4 over here. And that I don't need to compute all 4 nodes. I just need to compute these two nodes, the left and the right, and I get 2 plus 9, which is 11. And that's exactly what happens here if you calculate the whole thing. think you get 11 over here. Over here, I see 12 and minus 1. And so the sum of all nodes from 5 to 6, or rather from 5 to 8, is 12 minus 1, which is 11. And finally, extending this logic, we get the sum of all nodes from 1 to 8 is 11 plus 11, which is 22. And let's just try to see what happens. Minus 1 plus 3 plus 7 plus 2. And I'll just bring this down. 4, 8 minus 1. So that's 4 plus 8 minus 1 is 22. And you're seeing that the topmost node is actually answering for the entire tree. This node here. So all I've done is aggregate some information onto parents. Now the parents will be responsible for the ranges that they represent. Each of these parents has a particular range. So this node has the range 5 to 6. And this node has the range 7 to 8. Right? Now, if I'm asked to find the sum of all elements from 1 to 4, I can do that in one go. I can just come to this node and answer. All right. So before we do that, let's also try to figure out how do updates work here, because updates seem simple. If it's a single node update, a to x goes to, has to change to y. This is easy. How so? We go to the index x. I'm going to assume a of 3 is being changed to 5. So 3 is over here. And a of 3 is being changed to 5. So I'm going to rub this off and add 5 over here. Okay, I'm just going to rub this off and add 5 over here. I'll keep the old value so that it's simpler to understand. Now that this has been updated, the change has to be propagated up to its parent, because its parent is responsible for the entire range, which means as an element in the range has changed, the parent has to change its value. So from 9, it becomes 5 plus 2, which is 7. From 11, this is its parent, which needs a propagation again. From 11, it becomes 2 plus 7, which is 9. And finally, the parent at the root has to update itself, and that becomes 9 plus 11, which is 20. So you see a minus 2 happened over here. Effectively, 5 was replacing 7. So 2 was lost from the entire sum of the array and also from each of the subtrees that we have here. So that's how a update is propagated. All right. Is this efficient? Let's first figure out if our updates are efficient enough, because it doesn't make sense if our updates are going to be order n, right? Because then we have kind of defeated the purpose of making this entire segment tree. The update hits all the parents, all the ancestors of the node being updated. The number of ancestors that a node has is log n. And how do I get to this number? Well, the total number of nodes in this, let's figure out the total number of nodes in this. The last layer has n nodes. The second last layer has, every 2 nodes in the last layer is making 1 node. So the second last layer has n by 2 nodes. The third last layer has n by 4 nodes. The fourth last layer has n by 8 nodes, and so on and so forth till we have just 1 node remaining. All right, so effectively what we'll have is how much time does it take for n to convert to 1? That's the number of parents that we have, right? Because over here we had 1 parent, over here we had another parent, over here we had another parent, and so on and so forth. So the time required for n to get to 1 when being divided by 2 consecutively is going to be log n to the base 2. And you can see this because there's n raised to power, divided by 2 raised to power x is equal to 1. If you do the math over here, it comes out to be x is equal to log of n to the base 2. Okay, so the updates are pretty fast. That's what we have proven. We have a way to update our tree, and the updates are fast. So we are good here. The main problem is range queries. All right, I'll just check your. Okay, my reading speed is really good, so I just went through everything. For the range 2 to 3, there is no parent value. Oh, we'll get to that. We'll get to the point when we have a range query which is not perfect. I mean, basically, the range queries, the author of this question is not going to be nice and say 3 to 4. They're going to give something weird, like 2 to 6 or 2 to 5. This is the point when your segment tree data structure has to perform, right? So let's get to that. Now, okay, do we really care about the values? Yeah, I'll just use a new page, and this gives me -1. So it's -1 3 7 2 4 8 -1 0. So all right, let's see how good my memory is. Or even better is, yeah, I have them all here in the cheat sheet. Haha. -1 3 7 2 4 8 -1 4 8 and -1. So 0 is also here, but we'll get to the reason why 0 is not so important over here, because 0 is not adding any value. Of course, it can be updated, so yeah, that might change. So let's keep that. Now our segment tree was being formed this way. I'll just reconstruct it so that it's simple to understand how it was formed. Each of the parent contains answers for the entire range, so that it basically answers for. So this is -1 and 3, that is 2, 9, 12, and -1. They're 11, and this is 11 again. Of course, we had updated one of the nodes, but it doesn't really matter. The range query works even for updated nodes, of course. Now, what is the time required to construct this tree? Yeah, the time required to construct this tree, the first level, the lowest level, has n nodes. So that is n nodes that we need to touch. The second level has one computation, left node plus right node. And so that is order 1. And the number of nodes you have is whatever number of nodes you had here divided by 2, because every parent represents 2 children. So you have n by 2 nodes here, n by 4 here, and n by 8, dot, 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 all the way up to 1 node. So we saw that the time required to get to the parent is log n. But how many nodes do we have in total? Well, you have n plus n by 2 plus n by 4 plus n by 8 plus so on and so forth up to 1. This is a geometric progression. All I need to do is take n common, and I have basically, if I put 1 over here top, then I have oh sorry, I don't need to take n common. This is going all the way up to 1, right? So this is, I'll take n common and I'll get 1 plus 1 by 2 plus 1 by 4 plus 1 by 8, at most up till infinity. Of course, this is much smaller than infinity, so the number we are going to get here is going to be smaller than the approximation we'll make here. Okay, and this is a geometric series, which comes out to be, the answer for this entire sum can be approximated to 2. So 2 into n is the total time you'll require for constructing this tree. So order 2n is basically order n. So construction is also quite fast. Cool. So we have constructions fast and updates fast. We need range queries to be fast. Okay, let's see if I can get as much red ink out of the way so that the plate is clean. Perfect. Now for the main guy, the range queries. Let's take the range from 1, 2, 3, 4, 5, 6, 7, and 8. We take the range 2 to 5. This is the range query. Now you could think of starting from the bottom, but that defeats the purpose because you have to hit every node. So instead, the important thing over here is to go from the root and to touch only those nodes which might be responsible for the range 2 to 5. So I'm going to pass in the range 2 to 5. Now this segment tree at the root is going to tell me that, hey, this node answers for nodes from 1 to 8. if you're within my range, you can go around. If you have an intersection with my range, basically you should go to the left and right, because I'm not sure what the answer will be. However, if I entirely lie within the range that you represent, I'm going to answer immediately, right? And that makes sense, because when you look at it, every node is capable of answering queries for the entire range that it represents, but not for ranges which might be outside. So if you have an intersection which is not entirely the range that this represents, 1 to 8, then you need to go to the left and right. So let's just go there. Left and right. The left represents range from 1 to 4, and 2 to 5 has an intersection with 1 to 4. So it's an intersection. It's not completely within 2 to, I mean, 1 to 4 is not completely within 2 to 5. So you go to the left and you go to the right. Over here, you have the range 1 to 2. At 1 to 2, 2 to 5 is intersecting the range. It's still not completely within the range. All right. I think I kind of messed up over here. Okay. Well, we'll just redraw the whole thing, but I just need to draw the nodes, right? And we'll get to the values in a second. But the important part is the logic. So I'll draw the nodes first, and then we can answer. Okay, so we were at this point. I had said 2 to 5 is the range that I'm querying, and the tree itself had the range 1 to 8. We said that this is not entirely encapsulated, so we go over here to the left, which is 1 to 4. 2 to 5 has an intersection which needs range queries to both its children. 1 to 2 has an intersection, again range queries to both of its children, gives me 1 to 1 and 2 to 2 as ranges. Now 1 to 1 is the first thing. At 1 to 1, I know that 1 and 1 is entirely outside the range 2 to 5. So is there any way that the queried range 2 to 5 is going to be dealing with this answer over here, with this subtree over here? And the answer is no. So if it is no, what I need to return is a null value from this point, right? I can't return the answer over here, which was I think -1. So if I return -1 over here and the 7 over here, then that would be wrong. So I'm going to return a null value, and the null value in my case, because it's a sum query from x to y, what I need to do is I need to find a value such that sum of x comma this value, I'm going to call it I, which is the identity, is going to be x. Now what happens when you do x plus I equal to x? You basically understand that I is equal to 0. So in our case, the null value is going to be 0. However, if you were asked to multiply the left and right subtrees, that would be mult xy, or xi is equal to x, which means x into I is equal to x, in which case x would be 1. Okay, so this is what a null value means. Basically, you can return that, and it does not affect the answer. It does not affect the answer that you're looking for, the sum. So I'm going to be returning a 0 over here. All right. So it comes over here 0. Again, it goes to the right child because that had been queried 2 to 2. 2 to 2 entirely falls within the range 2 to 5. And so this parent goes no longer down the subtree. There is no space to go down the subtree anyways. So it just returns the value that it has, which is 7. So 7 is returned over here. This parent now condenses these two values, 0 and 7, to give 7 as the answer which will be sent up. Okay, of course, it's containing something else. It's containing, I don't really know what, but if this is the case, then 7 will go up. Now, when you come to the right, 2 to 5 is the range you're querying. 3 to 4 is the range that it completely encapsulates. 2 to 5 completely encapsulates the range 3 to 4. We should answer directly from this node itself. We should not go down this subtree. Yeah, because this node has the answer for both the elements within its range, and your range is completely encapsulated by the range which has been queried right now. So let's assume that the answer here is 6. Return 6 then. The parent then sees two answers, 7 plus 6, which is returned. 7 plus 6 is 13. You come to the right, and actually the segment tree is entirely messed up because I haven't actually written down values. So I'll just put in some fictional values: 4, -1, 3, and 7. Yeah, this is giving me 5. This is, or rather, it's giving me 3. This is giving me 10. This is giving me 13. -1 and 7. -1 and 7 should give me 6 here. 6 plus 6 is 12. And 13 plus 12 is 25. Yeah, this is the new segment tree. And we are querying for values. So as we know, 13 was returned from the left subtree using these values. I'll just ask you guys, does it make sense? Okay. That's the assumption. Okay. So anyway, at lazy propagation, we'll probably get this sorted. Now at 13, I have the answer from the left child. So the function will go to the right child. It's a recursive function. So I go to the right child. I see that the range is 5 to 8. Go to the left child, go to the right child. The reason for this is because 5 to 8 is not entirely encapsulated by 2 to 5. So I go to the right, and before that, I'll actually go to the left. So 5 to 6. 5 to 6 is not entirely encapsulated, but it does have some intersection. So go to the left, go to the right. 5 to 5 is entirely encapsulated by this range, 2 to 5. And so it will return the answer 4. While over here, 6 to 6 is entirely outside the range 2 to 5, and therefore it returns the answer 0. So effectively, this parent gets 4 plus 0, which returns 4. At the right child, I see that I have the range 6 to 7, 7 to 8, which is entirely outside the range. And this returns the identity, which is 0. At the parent, I see 4 plus 0, which is returned 4. And the final answer is 13 plus 4, which is 17. Now let's see if 2 to 5 gives us 17. This is the range. 7 plus 3 is 10. This makes it 13. And this makes it 17. So that's the correct answer. Okay. So a lot of you must be knowing about segment trees and range queries. Maybe you guys don't know about updates yet, lazy propagation, and that's an interesting thing. But before we get to that, just to explain the untitled 4, like what is the time complexity of this? The time complexity of this is log n. Now a lot of people know this, but they don't really understand how this came about. Like, how is it log n? The reason for this is when you're given a range, right? That range is effectively a number. The size of that range is going to be a binary number. In that binary number, you're going to have powers of 2, either set to 1 or set to 0. So the total number of nodes that you'll hit is going to be log of n, because you have broken the ranges into sizes of powers of 2. Yeah, this is the actual, like, if you go deep into this, then you will find out the proof right here. But I'll give you an even simpler proof. Just have a look at how the range behaves. I mean, how the segment tree behaves for different ranges. If you go for really small ranges, yeah, really small meaning range of a single element range. In this case, when you're going to the left and to the right, most of the right nodes, when you're going to the right, are going to fail. basically return you the identity function. And so you'll have saved a lot of computations on the right subtrees. Most element. In that case, the leftmost subtrees will start returning you the identity zeros. Okay, so a lot of computations are saved there. And effectively, you will be querying just one node. So that would be log n. You're querying few nodes. On the other hand, if you increase the range, yeah, you keep increasing the range from here, go to the right, go to the left. What effectively happens is, as you increase the range, you start hitting parents more instead of hitting the individual children. And if you increase it like all the way to the left and right most nodes that you can in the segment tree, then you are just going to answer at the root node itself. So the number of nodes you're going to hit is reduced even when you're increasing the size of the range. And effectively, the maximum number of nodes you're going to hit are again log n. So log n is a good bound that you have for any kind of range that you have in the segment tree. Yeah. So that's an intuitive explanation. However, you can find the answer in binary numbers because each of the parents represents a range and the size of that range is dependent on the level of that tree, effectively making this binary number of the range the number of computations that you need to do. Okay. Is everything fine? I mean, is everyone understanding what's going on here? Okay, finally, let's get to the difficult point, which is the range update. And then we can make a few announcements. Okay. How do I talk about the range update? So now I'll just go slow and explain how the segment tree has a range update. Okay, interestingly, if I write down the values -1, 7, 3, 4, 8, 2, and that's it. That's my array. Okay, so this is my effective array. If this is the case, what do I do? I mean, my segment tree is expecting a perfect power of 2, right? In this case, I can add zeros. So basically, I'm going to be adding identities to the last few elements. If you had multiplication like we discussed, it's going to be 1. And when I add identities, I'm not effectively changing the value of the parent nodes. Okay, so it's going to be identity over here. With 8 and 2, it's going to be 10. 10 and 1, 10 and identity is going to remain 10. So that's a special thing. I mean, that's a special case rather. 3 and 4 give me 7. This gives me 6. They both combine to give me 13. And finally, 10 and 13 combine to give me 23. Okay. Now for a harder question, which is range updates. From X to Y, so I'll take the assumption this node to this node, again, 2 to 5. Add 1 to them. Add the number 1 to all of these nodes. I think I'll take a better range. Yeah, 2 to 6. Add the number 1 to them. Or in fact, you can add any number. So I'll just add the number X to it. In the range 2 to 6. So this is my effective range. And each of these numbers need to be added with X. And X, in my case, is 3. So 10 needs to become, 7 needs to become 10. This needs to become 6. This is 7. This is 11. And this is 5. If you do this in the brute force way, of course, the order complexity comes out to be order n for the update, which is not feasible. So let's try to do this in the smart way, in the segment tree way. We come to the root node for the range update, 2 to 6. The same logic is applied. 2 to 6, what does that mean? It means that I have in my range 1 to 8 some nodes being updated. How many nodes? In my range, 2 to 6, And 1 to 8 is my range, and 2 to 6 is the original range. What is the intersection? The intersection is 1, 2, 3, 4, 5. 5 nodes. Yeah. So basically 6 minus 2 minus 1. This comes out to be 5. Or rather 6 minus 2 plus 1. So 5 nodes here. So 5 nodes have been added the value 3. What has effectively happened is my sum has been added with 5 into 3. Correct? So this is 15. So 23 plus 15 is my effective value. So I'm going to be updating my value. I'm going to be storing this 15 additional in my node. Okay, so my answer is 23 plus 15. If anyone queries me, I won't just return 23, I'll return 23 plus 15, which is going to be 38. Okay, that's the effective value. Now, just like in a range, update, rather range query, I'm going to be going to both my children because I'm not sure of the range encapsulated by 2 to 6 in my original range 1 to 8. So here I have 1 to 4, and here I have 5 to 8. Okay, original range is 2 to 6. 1 to 4, there is an intersection. What is the size of the intersection? You can see that in 1 to 4 and 2 to 6, I have nodes 2, 3, and 4 falling in this range. That's 3 nodes. But what you can do effectively is update the range. Like instead of passing 2 to 6, when you're going to the right child, pass the rightmost of either the query uh, or the range that you are handling. Right? So you will have, instead of 2 to 6 being passed, you will have 2 to 4 being passed here. Yeah, and this way you can easily figure out what is the intersection of the range. Okay, so 2 to 4 is passed in, 1 to 4 is the original range. How many nodes do we have intersecting? 3 nodes, quite obviously. So 13 will have an update of 3 nodes, having added the value 3, which is 9. Okay, so effectively 13 is going to be 13 plus 9, which is 22. Okay, and we'll see how this works out. Again, 13 does not know the exact, does not entirely have its range encapsulated by the original one, so we go down. And over here, we come to 1 to 2. 1 to 2, how many nodes does 1 to 2 have in its range? Well, 2 to 6, so it's kind of obvious. There's just one node, so it's going to update itself with a +3. So that is the lazy propagation bit. Okay, and we come to the left node. We see nothing needs to be added because this is 1 to 1, entirely outside the original range, 2 to 6. And so we do nothing over here, and we return 0. I mean, we don't need to return 0 because this is an update, so we do nothing. Just return the function. On the right hand side, there is nothing more to go. I mean, there's no other leaf nodes. This is the leaf node. So we just update this value from 7 to 10. Okay. Now let's come to the right. Yeah, because the function returns, goes over here, returns, and then it goes to the right. This node has the value effectively 22, right? Because 9 is over here. And at this point, what's going to happen is 3 to 4 is entirely encapsulated by the range 2 to 6. So it's not going to propagate this update down. It's just going to keep that update here. It's going to say, keep the update and tell me what is the change. The change is 2 nodes. So that is going to be 2 into 3, which is 6. So 6 is going to be kept over here. Okay. Is that making sense? All right. I think it is. And in fact, the thing about lazy propagation is that you can update values, you can update all values, uh, as long as you have an intersection. So every time there's an intersection, effectively what you do is you just send this value upstairs. This value also goes upstairs. So you don't need to do this on the spot, like the 9 that I added over here. It can be done through upward propagation again, but this is one way. It's an easier way to think of when you're going down. You just keep updating every node. Now coming to this node, because we have returned the function and it comes to the right. 5 to 8, 2 to 6 is what we need. So 2 nodes over here, this value becomes 16. We come to the left. Over here we have 2 more nodes, and you should not propagate downwards because this node entirely is encapsulated by the range that we have. So it's going to be storing 10 and the value 6. Similar to this, 7 and the value 6. Over here, 6 and the value 3. Rather, you can just store 9 over here. Yeah. Store 22 over here. And this function has still not returned, so we are going down. So we come over here. This is 10 and 6. Lazy propagation 6. And finally, when we return, this value changes to 38 because we have 16 plus 22, which is 38. Yeah, we could have done it on the spot, but you can also do it through returning the function. Guys, is this bit clear? Okay, and that is basically lazy propagation. Kind of an anticlimax, isn't it? Why is this special though? How is this actually helping us? Well, the range update took us log n time, just like the range query took us. But what is even more special about this is that what if you're next asked to query the range 5 to 5? Yeah, in that case, this node has not been updated, and if you use the simple update logic, you're going to come over here and answer 8, while actually the answer should be 8 plus 3, right, which is 11. So how are you going to take care of that? The only thing is when you're doing the range query, you go down, and at any time when you see an additional value here, right, and you see that this node needs to be queried on both sides, you split this value. You split this value onto both nodes. You go to the left, you go to the right, and you add plus 6. I mean, the value has to be 3 actually. That's the whole point. 3 has to be added to all values within the in the children. So 3 has to be added over here. 3 has to be added over here. This becomes 11, and this becomes 5. Yeah. So the original thing that I was talking about, adding different values, is not correct. You should be adding the value x to this node. That signifies that all nodes within it have been added by the value 3. So that's what's happened here. Similarly, if the range query is this range, when you come down over here, it's fine. The answer is 10. This is correct. However, over here, the answer should be 6. 3 plus 3 should be 6. So when you come to this point, 7 and 3. So when you're splitting over here that you need to add 3 to both its children. So 3 plus 3 will become 6. And over here, 4 plus 3 is going to become 7. So now your range is being propagated down lazily. And that's the reason why it is lazy propagation.